A very good noon to one and all. I, on behalf of the Science Club, extend a warm welcome to each one of you present here. Today, as a part of Science Club activity, we have with us an eminent scientist, Professor Uday Maitra from IIC Bangalore. Welcome, sir. I would now like to call upon the mentor of Science Club, Professor Gadre, to introduce the Science Club.
Okay, very good afternoon, ladies and gentlemen. I am doing this duty on behalf of Avinash Kumbar, who is the real boss of Science Club. I do normally things behind the screen. I don't do very active. Avinash is a very active participant. I mean, he really takes care of the whole program, so I'm doing it on his behalf. As you are aware, this is a new activity of the Savitribai Phule Pune University, which is running for about a year, little over a year by now. And we have had, if I just recollect, on July 22, we had Raghavendra Gadakkar. On August 19, we had Professor from TIFR. October 14, we had Professor Rohini Godbole. Professor M. Valiathan in the month of November, and then Professor P. Balaram in January. And now we have another distinguished organic chemist, Professor Uday Maitra. Uday is known to me personally for a very long time. We share a common IIT Kanpur background in some way or other. So I'll not take much time, and officially he will be introduced by our people, students, because this is an activity run for the students by the students. So our role is very, very limited. Only you can see what he has arranged on the table. And I am reminded of Linus Pauling, very beautiful quotation by Linus Pauling. He said that instead of making quantum mechanical calculations on ammonia, first let them smell a bottle of ammonia. Okay, you can do a nice calculation, but students should get a feel. This part was there in our culture, academic culture, when I was a student. Of live demonstrations in our college days. So I'm very happy that Professor Maitra will be showing you something very exciting, not video, actual, in person. And with, I'll hand it over to our anchoring people. We had introduced something simple. All student participants are welcome to see of the lecture and hand it over when they go out of the hall. This is not compulsory, but we encourage you to summarize the talk in about one page, what you heard from the speaker. Okay, so please take out your pens and papers and start jotting down as soon as Professor Maitra begins to talk. The best 2 or 3 notes will get a token of some kind. Okay, so with that, let me hand it over to.
Thank you, sir. To know a little more about Professor Uday Maitra, I would invite Sapna to briefly introduce sir.
Good afternoon, everyone. I feel honored to introduce Professor Uday Maitra. After his BSc from Presidency College, Calcutta, and MSc from IIT Kanpur, he got his PhD from Columbia University in 1986, working with Professor Ronald Breslow. Following a postdoctoral stay at the University of California at Berkeley with Professor Paul Bartlett, he returned to India and after a year at IIT Kanpur, moved to IISc Bangalore in 1989. His research interests are in the chemistry of bile acids, hydrogels, metallohydrogels, and organogels, and organic, inorganic, hybrid materials, enzyme sensing, etc. Professor Uday Maitra is among the first in India to initiate detailed studies on small molecule derived gels, which are an important class of soft materials. Very recently, his group has developed a general strategy for low-cost, paper-based, photoluminescent enzyme sensors. He is also greatly interested in chemistry education and is a regular participant in a variety of outreach programs for high school and undergraduate students. He has received a number of awards and honors, including the S.S. Bhatnagar Award in Chemical Science in 2001, and is an elected fellow of the Indian Academy of Science and the Indian National Science Academy. Thank you.
Thank you, Sapna. Without any further delay, I would request Professor Uday Maitra to begin with the
Thank you very much for the kind introduction. I would also like to, it says lamp dimming. It's okay? Let me start my timer so that I don't go off scale. Okay, so let me also thank Professor Avinash Kumbar and other organizers of the Science Club for giving me an opportunity to interact with you. Even though I had given this title for my talk, and later on I realized that since it's going to be an activity of the Science Club, I thought I should show some experiments. This will be in the last 20 minutes of my presentation. I'll spend about 40 minutes or so on the talk itself. And this will have nothing to do with the main title that I have described here. I should also point out to non-chemists here that my talk will be somewhat non-technical, and it's actually, even though I work in the Department of Organic Chemistry, the work that I'm going to present to you has a mix of organic, inorganic, physical chemistry, and a little bit of biology. So I hope that the work that I'm going to share with you will probably appeal to many of you. Before I begin anything else, today happens to be 17th of February, and let's try to remember what has happened on this day in the history of science. The first one is important to organic chemists because this gentleman named Bile, now of course you have everything at the tip of your, of your finger to access information, but for many decades, almost more than a century, people relied on the Bile volumes to look for information. It is sort of like the chemical abstracts, but focused mostly on organic molecules. And of course, many of you have studied the Stern-Gerlach experiment, and he was also born on this day in 1888. Since I'm going to talk about soft materials from bile salts, let me define the kind of soft material I'm going to speak about. These are materials which are known as gels, which many of you have seen and experienced in food and cosmetics. So my outline is an introduction to gels and bile acids. Then I will talk about metallocolloid gels. The red part I will skip completely. Then I will also tell you how this work actually evolved from a very simple observation made more than a century ago. This was in fact something that was not planned at all. It all started with a undergraduate student who came to my lab in the summer of 2010. But let me go back and give you a broad introduction on gel. So what is a gel? And gels, in fact, are things that, as I said, you all see in your daily life in the form of a toothpaste, shaving gel, and various other ways. But then it's also important to realize that many of the biological systems in our body also work on materials which appear to be gel-like. For example, in the joints between the two pieces of bone, there are materials which have gel-like gel-like consistency. The aqueous humor in the eye, and in fact the lens, the eye lens, is also primarily a gel-like material. Of course, it is much more complex than a simple gel. So in biology or in cosmetics, most of the gels which we deal with are made from polymers. In the biological system, these are largely proteins, and in synthetic materials such as shaving gels or a toothpaste, these are largely synthetic polymers. But in the last almost 30 years, small molecule derived gels have made a big space, have taken a big space in scientific research, primarily because the new techniques have developed in the recent past which allow people to study these gels, and also because these sort of gels have been found to be much more engineerable, I would use the word. In other words, you can fine tune them to have a certain kind of property. Okay, and that is something I will try to highlight by the end of my presentation. This is, of course, other kinds of gels that you also see. It turns out that the history of small molecule derived gel dates back to the 19th century. This is a paper published in 1841, and this is the first reported publication I could find where there was a mention, this in German, that using the lithium salt of uric acid under certain conditions, it had set to a gelatinous mass. Okay? But then this field remained dormant for many, many decades, and eventually the first book on gels, in which in fact I, along with my students and colleague, had a chapter. This book came only in 2006. So you can see 1841 and 2006 was the first book published in this area. So gels have many applications. As you have seen, the polymer gels have applications in cosmetics and in food industry, but small molecule derived gels can be tuned to form a variety of, to develop a variety of applications. Some of them I have listed here. And I will not going to talk about all of them, but I'm going to highlight a few of them. Okay? For example, you can use some of these for organic optoelectronics, can be used in biomaterials, in tissue engineering, for growing natural cells in a nearly natural environment, and so on and so forth. So I'll talk about a little bit about sensing with a particular class of gels. Okay? And these are somewhat old reviews written by my students. Let me now introduce you to the bile acids. Bile acid is a class of biosurfactant found in our body, and I will come back to the position later on. But you can see that in 1928, a Nobel Prize was given to Wieland on the chemistry of bile acids. Okay? But then those who are organic chemists would recognize that the chemical structure of the bile acid published in his Nobel lecture is actually not correct. Okay? The molecular formula is correct, but the chemical structure is not correct. So this is the correct chemical structure of the bile acid, and what happens is that these bile acids are essentially degradation products of cholesterol. So they are formed in the liver and stored in the gallbladder in the fasting state. Like, you are all waiting for lunch, right? Lecture to be over and go for lunch. So now all your bile salts are accumulated here in your gallbladder and will start to flow once the food comes into the upper part of the small intestine. Basically, the bile acid has a shape like this, my closed fist, with the top being non-polar and the bottom has polar with a variety of hydroxyl groups. And what is important is that the number and position of the hydroxyl groups essentially tells you where the bile acid is coming from. In other words, you can almost pinpoint the source or the species from which the bile is coming by analyzing the bile acid chemical structure. In other words, human, bovine, reptile, birds, they all have different structures of bile salts. Okay, so that makes them quite interesting. And as I said, they perform a number of physiologically important functions, the most important being the digestion of fat. Okay, fat is insoluble in water, as everybody knows, and in order to digest fat, you have to emulsify that. And bile acids or bile salts, along with phospholipids, play an important role there. Okay, so in the last several years, my group, or decades, perhaps a couple of decades, my group has utilized the bile acids for a variety of applications. Some of them were designed, some of them were serendipitously discovered, and I will talk about one of these in the next 20 minutes or so. So, and this sort of bridges this hydrogelator and materials area. Okay. So let me tell you that the molecule of today's discussion will be only one particular bile acid, where it is a trihydroxy bile acid, X is OH. It's a chiral, naturally available biosurfactant. And as I said, unlike normal surfactants like we use in soaps and detergents, it has got a facial amphiphilicity. One face is hydrophobic, one face is hydrophilic with 3 hydroxyl groups. Now our interest dates back to a paper published in 1914 when this British author said that if you take the sodium salt of cholic acid, that was known at that time, even before the Nobel Prize was announced, if you mix it with the calcium salt, it forms a clot. And the clot was nothing but a gel-like material. Okay? And we repeated this experiment, sodium chlorate plus calcium chloride, 100 years later, close to 100 years later, we found that it forms a nice gel, nice clear transparent gel. Okay, that was the old observation, essentially we repeated. Then our question was, can calcium be replaced by any other metal ion? Because as you know, calcium is very useful for the human body, but calcium is pretty unreactive. Can we replace the calcium by something else? And if that metal ion forms a gel, we can do a lot of interesting chemistry. Okay, that was basically what we initially thought. And I will not go into the details of the initial part of the work, because a quick answer to that is yes. Okay, so we published almost 6 years ago now, first report of monovalent, divalent metal ion and cholic acid. When they mix together, they form gels. Okay, so I will not go into those details. These are some of the papers we published from that area, and today I am going to focus only on a few of them and a little bit of unpublished work which focuses on a specific application of this gel. Okay, and now that we know that other metal ions form gels, then we came up with this following idea. A number of years ago, this was almost close to 20 years ago, we showed that this kind of a tripodal derivative molecule, it forms a nice gel. And one of the things that characterizes all gels, polymer derived or small molecule derived, is that they form this kind of a nanofibrillar material. Okay, so basically you get one-dimensional aggregates which are entangled to form a three-dimensional network. It is sort of like a ball of cotton. Okay, if you dip it in water, it soaks a lot of water because it has large surface area. Similarly here, the large nanofibers, which you don't see in your naked eyes, with your naked eyes, but they essentially have a large surface area, and the solvent molecules stick to that and cannot move. Okay, and at that time we showed, using a polarity sensitive probe, what I mean by this is that this molecule called ANS, it shows high fluorescence in a non-polar medium and zero fluorescence in a polar medium such as water. We doped this gel with this material and showed that the gel became fluorescent. Okay, but when you melt the gel, these gels are thermally reversible. Many of them are. This one was. When you melt the gel, the fluorescence goes. And that suggested that this molecule probably is residing on a hydrophobic environment. In other words, it is experiencing a hydrophobic environment in the gel, and we thought that this is probably sitting on the fiber. Okay, these are on the nanofiber. Then we thought that can we make 2 plus 2 in the following way. Suppose we are able to make a gel with a lanthanide and also add one more aromatic group. Then can we have a situation through self-assembly? You know, this is like almost like alchemy. Can you mix things together to form a gel and have the gel and essentially impart a property to the gel? Okay, that was the idea. So here the idea was that can we make a lanthanide cholate gel and dope it with a sensitizer, so in such a way that we will excite the sensitizer, this will transfer the energy to the lanthanide, and lanthanide will emit light. Lanthanides are, for those of you who have studied lanthanide and those who have not studied, lanthanides are important photoluminescent materials, but they do not show photoluminescence in water because the water essentially quenches their luminescence. So what people do typically is to cover the lanthanide with a lot of inorganic compounds or with a ligand, and then attach some sort of an antenna so that the antenna absorbs the light, transfers it to the lanthanide, and the lanthanide emits. But for doing that, you need to build or synthesize this entire package. And we try to avoid it by using this self-assembly process. We said that we will use commercial materials, mix them together and see whether the gel becomes luminescent. So first of all, we showed that all the known lanthanides which you can buy, which are non-radioactive, they all form gels. Okay. And then we thought that we will choose europium and terbium because europium emits in the red, terbium in the green, and these are in fact present in all these fluorescent lamp coatings, the white material in the fluorescent lamps. So these are very common lanthanides, and we thought that we will now make a gel with, let's say, europium cholate and add a non-covalently bound sensitizer and see whether this energy transfer happens. So this was again a shot in the dark, okay? But to our pleasant surprise, what we found is that when calcium cholate was doped with pyridine, calcium is non-photoluminescent, so you don't expect any fluorescence from calcium. You will only see fluorescence from pyridine. And you do see fluorescence from pyridine. Can we have this light off? You see the blue fluorescence from pyridine, so no surprises here. But the moment you change, yeah, that's nicer. The moment you change calcium by lanthanide, by europium, you see this magenta emission. Okay, that is because europium is emitting in the red, and there is a little bit of a residual emission from pyridine, and that is giving a magenta emission. And if I do not use pyridine here, I do not see any emission at all, indicating that the hypothesis that we had, that by a self-assembly, we have a system where the antenna absorbs the light, transfers it to the lanthanide, and lanthanide is emitting. And very quickly, I will not go into the details because these are all published. We found that 2,3-dihydroxynaphthalene was able to sensitize terbium, giving the characteristic green emission. And we also showed that by color, you can color tune these materials by mixing different amounts of terbium and europium, because terbium to europium energy transfer can also happen. And at that time, we became a little greedy because a lot of people were talking about white light emission. They still talk about white light emission. And we thought that maybe we can mix blue, green, and red, the standard RGB colors, and get a white light emitting system. Okay. Again, this work has been published, so I will not go into the details. This is how the gel looked like, the white light emitting gel looked like in ambient light, and under UV lamp, it showed a clear white emission. Okay. And these are some of the details of that material, and I will not go into that because it was published in 2015, and this is not the main part of the talk that I'm going to highlight today. But the main theme is that this particular simple-looking naphthalene derivative, I think all of you can see that it is nothing but 2,3-dihydroxynaphthalene. Now, this one sensitized the lanthanide, okay, in particular terbium, all right? So the question that we came up with is that can we use it for designing an enzyme sensor? Okay, and the idea is the following. As you know that, if you have certain kinds of diseases, then sometimes the blood is checked for the level of various enzymes in the pathological labs. For example, those who suffer from pancreas-related problems, amylase and lipases levels are checked. Certain kinds of liver diseases have corresponding enzymes, certain specific enzymes which are tested. But all these enzyme testings are done by very specific techniques. Some by colorimetry, some by fluorescence, some by other techniques. So we thought that this gives us an opportunity to detect all enzymes with the same device. Okay, and I will show you the idea or the hypothesis. And let's assume this is the dihydroxynaphthalene, which I will call as a sensitizer. So this will sensitize the lanthanide in a gel. Suppose we attach an enzyme cleavable group to it and call it a pro-sensitizer. You might have heard about drugs and pro-drugs. So it is like a pro-sensitizer, which is one step removed from sensitizing the lanthanide. And suppose when I mix it with the cholate, the lanthanide, and form a gel in the presence of this, if this does not sensitize the gel, then I have a very nice way of detecting the presence of a specific enzyme, because once I add the enzyme, specific enzyme, it will remove this part and it will liberate the sensitizer, and now the gel will become photoluminescent. Okay, so here the idea is that for every specific enzyme I have to make this pro-sensitizer, but in the end all the enzymes will be detected by the same green color. And we thought that that's a very significant enhancement in the techniques because you need to have only a readout of a green emission. Okay. All right. So how does it work? So what we thought, we will focus on the pro-sensitizer which has to be synthesized. And since we are dihydroxynaphthalene, and this is something Professor Dhawale would appreciate, we thought we will attach sugar units there. All right? Because a number of glycosides are known. Glycosides can tolerate a lot of substrates or substituents in their 2 position, and many of them are biologically important enzymes. Okay, so I'll show you. The details are not very important here. Okay, so let me show you an enzyme called beta glucosidase. Okay, this is the crystal structure from the database, but the deficiency of certain kinds of beta glucosidase causes certain specific diseases. Again, these things are not very important at this time. So what we did, again the synthetic part is also I will skip because these are all very routine syntheses, but the idea is that we take a glucose and attach this dihydroxynaphthalene. The idea is that this should not sensitize the gel, but upon the specific enzyme which cuts this bond, I will have the dihydroxynaphthalene liberated, so the gel will become photoluminescent. Okay. Similarly, this is a beta galactosidase, and lack of beta galactosidase in fact is found in most Asian and many Indian older men and women, because those who have problem drinking milk, okay, and it causes stomach upset, sometimes formation of gas and things like that, is because of the lack of beta galactosidase, or sometimes it is also called lactase. Okay, and nowadays we will also see Amul sells a milk called the lactose free milk, okay, which doesn't cause this problem. So the lack of this beta galactosidase is actually important to recognize. So again, same molecule was made. The only difference is that the stereochemistry here, but let's not go into those details today. And I will show you some data. So this is the galactosidase derivative that we measure, that we prepared, and as you can see, it is not sensitizing the gel. Gel is not showing any emission. Okay, but we add the enzyme, and immediately it starts to become green. And these are pictures taken using a readily available 365 nanometer UV lamp. Okay, no high-tech device needed for this, at least to get a yes/no answer. All right. So we thought that is interesting. There are some technical details here, which essentially shows you how the intensity of this 544 nanometer light increases with time. And you will also notice that if I don't have the enzyme, or if I have the denatured enzyme, and I am sure all of you know that upon heating to close to 100 degrees, all the enzymes get denatured. With the denatured enzyme, this reaction doesn't happen. Okay, so that means that the reaction is indeed happening the way we expected. And I will show you just one more example of alpha glucosidase, because alpha glucosidase inhibitors are known as, some of the alpha glucosidase inhibitors have been used as anti-diabetic drugs, okay, because they slow down the metabolism of sugars. So very recently we have made this alpha glucosidase derivative. The difference here is basically stereochemistry, that is only for organic chemists, that is whether it is down or up. Okay, so this is what makes an alpha glucoside, and Shruti, my student, has shown that indeed in the presence of alpha glucosidase, it shows the characteristic green emission, indicating that it is specific for this. We have done some testing with different enzymes. This is again similar sort of experiments done with a denatured enzyme or without enzyme, and that also worked out okay. And this is one experiment to show that the same enzyme having 3 different substrates. You know, here it is down, here it is up, and here it is up, but the hydroxyl group position is different. So again, you see response only when you have this one. Okay, and we have done a complementary experiment which I would not like to show you. But then the problem is, if you the way I have described the experiment, again the detection system is easy, but the procedure is a bit complicated. Okay, so we thought that these days most people are going for simple paper-based devices for detection. For example, many glucose testing kits are available, which are essentially electrochemical techniques but based on a paper strip. So we thought that can we do it on a piece of paper? Okay, and the reason for thinking along those lines was that these gels or gel-like materials, when dried, okay, when you dry a gel, the material that you are left with is called a zero gel, zero spelled with an X. Okay, so that zero gel showed emission, had the same emission characteristics in the solid state. Okay, which is good, which means that the structure, the fibrous structure is retained in the solid state. So what we did is to take, for example, filter paper. This is a scanning electron micrograph of normal filter paper, okay, where you see the cellulose fibers. These are micron size fibers, much bigger. And to that we add the gel which contains the substrate, specific substrate for the enzyme. Okay, I call it pro-sensitizer. And in this resulting SEM image, what you see is that there are flakes form from the drying of the gel, and they are embedded into the gel fiber. So we have a piece of paper which has the detection system integrated into it. All we need to do is to add the enzyme and see what happens. Okay, and we found out by doing certain other experiments, detailed HPLC experiment, that indeed the chemistry is happening on the filter paper. The enzyme is able to cleave the substrate on the filter paper. Okay, again I will skip these details, okay, because that is again additional technical information that you need not know at this time. What we eventually were able to show is that, for example, these sort of paper strips, okay, which we make on the, we basically take very high-tech gadget, this black chart paper, make holes using an office punch, okay, and stick filter paper on the back side, okay, so that you have this little white spot on which we spread about 40 microliter of the gel, and upon adding the specific enzyme, it starts to show a green glow. Okay, and we showed, for example, using beta glucosidase from raw almond. Almond nuts contain glucosidases. Okay, so using that you can show that in the controls, these are the two controls. One is no enzyme, no extract. The other one is a heated extract. But in the presence of a natural extract from almonds, you can detect the enzyme. Okay, and it lights up. You can see that the green color here is much more intense. We have also shown, for example, this is an inhibitor. I think Professor Dhavale has also made several inhibitors of glucosidases. This is an inhibitor I obtained from Professor Vankar of IIT Kanpur, and we were able to show that you can in fact detect these sort of inhibitors by this paper-based assay system. Okay, and here is a real example of using a biological fluid. For example, this is a different enzyme, collectively known as lipases or esterases. We showed, for example, in the presence of, this is a blank, and in the presence of blood serum, which has a lot of lipases and esterases, you can see this disc starts to glow. Saliva has much less amount of these enzymes, and in 10 minutes or in 40 minutes, the intensity becomes much lesser. So you can also, to some extent, qualitatively say what is more, what is less by this process. Okay. So in the end, I would like to summarize this part by saying that we have developed a very simple, based on a very old observation, we have shown that not only can you make these lanthanide-derived systems photoluminescent, but you can use them in a very creative way by adding a specific enzyme substrate for detecting enzymes. And when we submitted it for publication, the journal editor said that, you know, you are using expensive materials. What is the cost? And we actually worked out the cost, including the students' time spending for making the synthesis. We showed that 5 of these discs can be made for only 1 rupee. Okay, and only the lanthanide is the most expensive part. About 70 paisa goes into the lanthanide. The rest of it is only 30 paisa. Now what we have been trying to do is the following. You know, these discs, what we do is that we can either take a photograph under the UV lamp, okay, and see the images. But to quantify, what you need to do is to put it in a, either put these material in a plate reader, which is an expensive equipment, costs about 15 to 20 lakhs, or we can take a photograph, put it in the computer, and analyze the relative intensities using a software. So very recently what we have tried to do, this is work in progress, is to develop a small mobile phone like device which will have a slot for putting this paper disc in it. Okay, and then instead of this white LED, we will have a UV LED. Okay, and a touch screen, and which will have a software not only to fire the lamp, take an image, but also process it and measure relative intensities. And if we have a standard plot, which biologists would know what I'm talking about, using a standard plot, I can find out the actual intensity and map it onto a concentration level. So this is something we are trying to work out with a company to develop this kind of material of a device. And we believe that if we have the right kind of hardware, we should be able to do it. A prototype has been made which seems to work pretty well. And someday perhaps you will end up buying one of these things. Okay? It should be a mobile-like device and should not cost more than a mobile phone. And of course, this the main contribution of the main sort of scientific contribution comes in the development of a specific substrate for the enzyme. And we are now looking at enzymes which are pathologically more important to analyze, to assay, and work with some of the pathological laboratories to see whether we should develop specific molecules, specific substrates for specific enzymes which are commercially also important. Okay. So with that, I would like to close this part of the presentation. But before I do that, I would also like to show you that you do not necessarily have to have this enzyme substrates. There are some naturally occurring materials, naturally occurring materials and some synthetic drugs which can also sensitize the lanthanide. Because what we have is a dihydroxynaphthalene. Okay, and our idea was that if we have a naphthalene skeleton and a ligating group, such molecules should be able to sensitize the lanthanide. And interestingly, we found that naproxen, which is a very standard painkiller given for arthritic problems, I may have to take it very soon, that causes sensitization of the gel. So this is how the gel looks like in the absence of anything. But if you add naproxen, or this is a central nervous system acting drug called propranolol, these two would sensitize and will make the gel photoluminescent. But closely related drugs, ibuprofen, which is known as Brufen, one of the trade names, or atenolol, these things do not have naphthalene rings. They have only phenyl rings. They do not sensitize. And what we showed is that you can indeed detect these things in the blood using, so no sample pre-processing is needed, no background noise. We can make the gels only from commercial ingredients. And this assay is selective, sensitive, and rapid. And we can detect these two medicines in less than 1 part per billion concentration. Okay, so this is one thing. And more recently, this is published last year. Something that we have not published yet is, these days there's a lot of talk about antioxidants found in tea. And one of these antioxidants found in tea is a basically gallic acid derivative known as EGCG, epigallocatechin gallate. Okay. What we have found is that this EGCG can also sensitize the gel. This is the gel itself, and this is gel made with either gallic acid or this EGCG. And with this we have shown that indeed you can distinguish between green tea and black tea. Black tea has very little amount of this, as shown here in this plot. This B1, B2, B3 are black tea samples. This is blank, and this is a white tea. White is a very specialized kind of a tea, not found everywhere. And these are 3 samples of green tea from 3 different sources. So we now have a technique to distinguish green tea versus black tea extracts and their antioxidant content. And we are again trying to quantify this one. Okay. So this is the end of my scientific presentation. I would like to thank my students who seem to be spending more time on the small screen than in the lab. I hope they are not doing this thing now. This is actually a fake photograph, okay? But that's right. Okay. So I need to thank them for all the work that they have done, which I presented to you. And I would like to thank the DST and Indo-French Center for financial support. So before I thank you formally, I would like to now switch over to the second part of my presentation. Is that okay? I'll need another 20 minutes. Is that all right? Okay. So the idea here is that, in many high schools, many colleges, the practicals that they do are somewhat unrelated to the principles they study. Okay, at least in schools. So certain experiments which are very trivial to do, as I will show you here, if I can do it, everybody else should be able to do it. Such experiments are never done. Okay, you hear about a principle, but not the supporting experiment. So I'll show you 5 simple experiments which I think should appeal to all of you. Most of you know what the experiments are, but my idea is that you should probably take some of these things to schools and show it to school children. Maybe if you have siblings, you can show it to them. If you are teaching in schools or colleges or what part-time, you can show it to them and perhaps develop some of these experiments further to make things a little bit better. Okay, so before I do that, let me ask you a question. Okay, this is again something to do with real life. Can I have all the lights off here? This is something that everybody studies in class 6 or 7 in history books, right? What about this? All of you have studied about the reaction. This is actually a reactor, okay? The reaction that goes inside. And if you want a scale, all pictures should have a scale bar. And here my scale bar is Professor Sujit Roy of IIT Bhubaneswar, who is about 5.5 feet. Okay, so that's my scale bar. So you can guess it's about 30 feet long. Okay, and it carries out a reaction which is of great importance to humanity. All right, I'll come back to that with the answer a little bit later. Okay, so what I would like to do is to show you a few presentations of experiments which can help you learn some chemical principles. Okay, all right, so I would like to thank, I hope I have got all the names right, my student Deepankar who made this, who packed this dabba for me. This is the export dabba, which is what I call it. And I should thank students of this department. Names are given here. I hope I have not missed anybody who helped me set up everything else. And also Merck Sigma Aldrich, because I use some of these chemicals which are pretty expensive. So knowing my hobby, Merck Sigma Aldrich gives me some of these chemicals free of cost so that I can do the experiments. All right. First experiment is about chirality. Okay. All of you have studied stereochemistry and chirality, so I don't want to get into those details. One point I would like to highlight is to ask the students, okay, who are chemistry students, this is the trigonal bipyramid phosphorus. Okay. Somehow we keep organic stereochemistry and inorganic stereochemistry separate. Okay. But I think that should not be done in 2018. Okay. Because a molecule is a molecule, whether it has a carbon or phosphorus or sulfur or what have you. So my question is this molecule chiral? Answer can be only yes and no, not maybe. It's not chiral. 1, 2, 3, 4, 5, they're all different. So it has to be chiral, right? Okay, that's question 1. Question 2 is that for a tetrahedral carbon, if you interchange any 2 substituents, what do you get? For a tetrahedral carbon which has 4 different substituents, if I interchange any pair, what do you get? You get the enantiomer, right? Is that true for phosphorus? If I interchange 1 and 4, what do I get? I do not get the mirror image, I get a diastereomer. Okay, so the property that exchange of any 2 ligands gives the mirror image is only true for tetrahedron and for no other geometry. Okay, this is something that is often missed out in our understanding. One other thing you have all studied, that R and S enantiomers, they can be detected by their optical rotations, right? But also by their smell. Okay, because this is R-limonene, which smells like orange. S-limonene smells like turpentine or pine. One more example, this is called carvone. This one smells like mint, pudina. S-enantiomer smells like caraway seeds. You have all seen this in stereochemistry books, right? Okay, but do you believe these are true? So, I say seeing is believing, but as far as chiral molecules are concerned, I think smelling is believing. Right? So I would like you to smell. This is R-limonene and this is S-limonene. So my suggestion is you take R-limonene in your right hand, smell it, take S-limonene, smell it and pass it on to the next person. Okay, so it can go this way. R, S. And for the other 2 samples, carvone, I will start from the other end. Or maybe from Professor Gadre. this side and it can go this way and then come back later on. Okay. So this is R carbon, smells like pudina. S carbon, no, right hand. Okay, this smells like jeera, specific kind of jeera seeds, caraway seeds. Okay, so this is something that can be done very easily. Okay, students should be able to smell and difference, see the difference by smelling, and not by simply text, that says, okay, this is different and that is different. All right, that is one experiment. The other experiment I would like to tell you is about optical rotation. I think all of you have used or seen a polarimeter. How many of you have not seen polarimeters? Everybody has seen polarimeter. Okay, then maybe I should not do this experiment. But but let me illustrate that this can be done in a high school setup very easily. And as you know that you have a sodium lamp light passes through a polarizer, and if you put two polarizers cross, you will not see any light here. Okay, that's basically the principle. But nowadays, as Professor Dhawale has one in his lab, you can put a sample and get a reading on a display. Okay, all right. But there a lot of electronics are there. But I would like to show you, for example, if you put glucose in between, it will rotate the plane of polarization to the right or left, and then in a cross polarizer, when light was supposed to come, no light will come. Okay, and therefore you have to rotate it. So let's do this very simple experiment. All right, for which let me first of all blank the slide, this one. And these are no lights. No lights, please. I need this one and sugar solution. Okay, and I would need a couple of student volunteers to come here and show the experiment. One more. Okay, all of you can see this spot. Come here, Vishwanath. Come. Please hold this. One more. One of you come here. Now you sit down here. Okay. All right. So these are two polarizing discs. Okay. They are not very high quality, but and right now in this orientation, they are both parallel. So I put one here. Light intensity is cut a little bit. I put another one parallel. Okay. But you see, most of the light is transmitting. But I rotate the top one by 90 degrees. Intensity goes down. It's not completely cut off because these are all relatively cheap. So what will happen is, if in between I will put sugar solution, it will become more lighted. Okay, that means because the plane of polarization will be rotated. So you hold it here. Hold it here. And let us see how it looks like when I have this is our cell, measurement cell. Okay, so I keep it perpendicular and practically no light comes through. Right? So I keep it in the same orientation, no cheating, and put sugar solution here, glucose solution. Okay, now your job is to come and, can you come here and hold it? Now you see light is passing through. Okay, no problem. But when I put the second one, light is passing through because the plane of polarization has been rotated. And now if I put it clockwise, I'll get the null point. Right? So which means glucose is dextro-rotatory. But there is something more that will happen. Look at the color. Do you see different colors? And do you know why that happens? Because every experiment I ask questions. Okay, I think your job is done. Okay, so thank you very much. You know what happens is that this is not a sodium D light. Sodium D light is monochromatic. I'm using white light. And there is a phenomenon called optical rotatory dispersion, which means that light of different wavelengths are rotated by different angles. Okay, the optical rotation is different for different angles. So what happened when I had the one polarizer at the bottom is that the plane polarized light of different wavelengths got rotated by different angles. And then when I put the second one, I was essentially filtering out lights of different wavelengths. And that's why we saw colors of different kinds. But of course, overall the light got rotated clockwise because it is glucose and it is dextrorotatory. Okay, so this proves glucose is dextrorotatory, which of course everybody knew. Okay, but by using a white light, the advantage is that you show the phenomenon of optical rotatory dispersion as well. So let's move on to the next experiment, which is this I show only high school kids. Okay, so this is really an experiment on catalysis. I don't know if you have seen any catalysis experiment. Now let's have the lights. Have you seen any experiment on catalysis? Have you done any catalytic reaction in the lab? I'm talking only to the MSc chemistry students. Okay, hydrogen peroxide is a thermodynamically unstable and kinetically stable liquid. It is of course thermodynamically unstable because it has a weak OO bond, and that does not decompose, but iodide can make it decompose. Okay, so we will do this experiment and since oxygen is coming out here, to make the experiment a little more entertaining, I will mix the hydrogen peroxide with some liquid soap. Okay, so that the bubbling oxygen, okay, I need to open this. So the bubbling oxygen will produce a lot of foam. Okay, so that's the liquid soap part of it. And let me just be careful with hydrogen peroxide, which is kept here. And again, thanks to Vishwanath and everybody else who have helped me with this setup, I will add a good amount of hydrogen peroxide and put this fellow back here. I need the hydrogen peroxide for something else, but a little bit later. Okay, mix it well. Now, if I add sodium iodide and it forms a foam, it comes out like a toothpaste. Okay, that doesn't prove iodide is the catalyst, right? Because it can also be that the sodium is the catalyst. So we'll try to prove that one. Okay, by the way, whoever ends up cleaning this beaker and this mess, the purpose of having the tray is because I'm going to generate a mess. Okay, and I think you have weighed out sodium bicarbonate, but I'll add a little bit from this. Okay, whoever cleans up this mess will have to be careful because it is very corrosive to the fingers, to the skin. Okay, I add sodium bicarbonate and nothing happens, which means sodium ion or bicarbonate is not a catalyst for this. Okay, but then to this 1 gram of sodium iodide, I will add a little bit of water to dissolve it. This way the experiment works better, very nice. This is really an experiment on catalysis, as I said. Okay, so this is sodium iodide, just to confirm. Okay, you should always read the labels. All right, are we ready? Let's see what happens. And here comes your toothpaste. I think the soap is a little more dilute. I should have added a little more soap so that it really comes out as a toothpaste. But this is basically what you see is a decomposition of hydrogen peroxide catalyzed by iodide. And what you get is oxygen. If you have a piece of wood which doesn't have flame but is red glowing, and if you put it inside, okay, it will catch flame. Okay. Again, student can be taught that this is oxygen because it supports combustion. And in a converse way, you can do a similar experiment which will be mixing vinegar and baking soda and show that actually stops the burning process. And you can see that it is still coming out. Okay, so this is a very messy but experiment known as elephant toothpaste experiment. All right, next one. It's actually quite important. I may take another 10 minutes. Is that okay? All right. No more than that. This is something that you start reading from your high school days, right? in SN1 reaction, SN2 reactions, which one is more reactive, why it is more reactive, and so on. But has anybody here seen this reaction being done? It's very easy to do. Suppose I want to show you which one reacts faster in an SN1 reaction. Which experiment shall I do? I'm going to do it here. So tell me what experiment I should do. Since I can do it here, it is very easy to do, right? So think about the reaction. Reaction is a protic solvent. SN1 reaction means that you have a non-nucleophilic reagent, highly polar protic solvent like alcohol. Okay, what is the reaction product? HBr. So all I need to do is to find out where HBr is produced faster. And how do I do that? Again, your first year BSc. All right. So what I'm going to do is to set up 3 measuring cylinders here. Okay. And you might remember that bromide can be detected by first year BSc. Silver nitrate. This aluminum foil should tell you that I have something photosensitive, right? Silver nitrate. Only problem is I am not doing the reaction in water, because in water these alkyl halides are not soluble. Okay. So Vishwanath has prepared a solution of silver nitrate in methanol, and I am going to put about 80 ml in each of them. Okay, roughly. This is again a very rough experiment, but this can be designed as a kinetics experiment. I will tell you why. Because you can change the concentration of silver nitrate, you can change the concentration of the alkyl halides and so on. Okay, so I have roughly equal amounts of these 3 materials, which is nothing but silver nitrate and methanol. And my export dabba from Bangalore had all these 3 reagents. Okay, so tertiary, secondary, and primary. So I'm going to add these 3 liquids to this methanolic silver nitrate. And what would be the observation? If the reaction happens, I will generate HBr, and therefore I will start seeing precipitation of silver nitrate. Excuse me, silver chloride, bromide. Okay, primary, no reaction, right? This is secondary. And I think this reaction should be done for high school students when they learn SN1 and SN2 reactions. Okay, very easy to do. Secondary, no reaction, right? I hope the reaction with tertiary goes. Tertiary, okay, everybody can see, even in this large classroom or lecture hall, that silver bromide, what you observe is precipitation of silver bromide, and that is because HBr is produced, and that is because tertiary halide is undergoing a very rapid SN1 reaction, right? Done. Other corollary experiment I am going to show you is that, this is also something that everybody studies. Bromide and chloride, which one will undergo solvolysis faster? Chloride, right? For this one, what I am going to do is to have a slightly different method, and I will detect the H+. Okay. Now you will see that tertiary has reacted, primary is not reacted, secondary is starting to get cloudy. Okay. If it becomes little more cloudy, and when it becomes little more cloudy, I will stop. Okay. That also acts as my timer. But for the other experiment, what I am going to do is to use a little bit of methanol. I am actually doing it quite rapidly. I have only 2 more experiments to show you. But if you are tired, I can stop anytime. Shall I stop? Are you sure? You are not hungry? But you have all the bile acid accumulated in your body, in your gallbladder. Okay. Let me just make sure that I have poured roughly equal amounts in each of them. Okay. And this time the experiment will be by adding a universal indicator. This universal indicator is available from domestic suppliers. So I add Oops, sorry. Small amount here and a small amount here. Okay. And in chemistry, it is very important that you clean your mess as you are going along. Okay. Don't leave the mess for too long. All right. So this is the universal indicator in methanol, which has a particular color. Okay. And I'm going to add the chloride and the bromide separately. And what you will observe is the following. If the hydrolysis happens rapidly, the universal indicator will change the color. This is the chloride on your left. Okay? And bromide on your right. Watch carefully. Something is happening? Maybe I should put a white background behind. You can see that the bromide has reacted much faster than the chloride, and because the color has changed, if you measure the pH will also be lower. And these sort of experiments can be very nicely set up. You know, if you have a spectrophotometer, you can change the concentrations, measure the rates of reaction by looking at the absorption spectra changes between this and this. But visually, it's very easy to do, very easy to excite undergraduate students or high school students to demonstrate that these things are indeed happening the way they should. And you can see that the secondary, it's not the secondary does not react. It is becoming cloudy, okay, like fog in the early days of winter. And primary will also react, but very, very slowly. Okay. Let me now quickly go to the last two experiments. Okay. You all have studied this thing, absorption and emission of light, right? Right now, I want all the lights to be switched off. Okay. And what I show on the top is essentially absorption of light, and you all know Lambert-Beer's law. The second one is emission of light, fluorescence, and where you absorb one color light and then you emit a different color. Okay, and this is an experiment that can be shown very easily, but I need a monochromatic light. Do I have a source of monochromatic light here? Laser pointer, good idea. So I have a green one and I have a red one. Okay, and for this, again, the requirement is very, very simple. I'm going to use up some of this water. Okay, and water is colorless, of course, and you can see that there are some bubbles, right? And because it is transparent, my green laser will not show any absorption, right? No green light absorption, no red light absorption, because otherwise it would have looked colored. All right. And for showing this interesting fluorescence experiment, what we are going to do is to excite something which absorbs green light and we'll get yellowish orange light out. Okay, that's basically the principle of fluorescence. And all you need is a 20 rupees worth of a pink highlighter, because all these pink colors come from a dye called rhodamine or rhodamine type dye. Okay, so I'll use a little bit of this thing, shake it up here, and I'll show you with the white light that I have the dye at the top. You see the dye at the top? All right. Now instead of white light, if I pass the beam of the green laser, you see the emission from the top. Okay. If you are not able to see it properly, I will add a little more dye here. Okay, and mix it up. Oops. Let me just clean it up a little bit quickly. And again, my reference is always the white light. You see this dye, right? You see that. It's actually showing some fluorescence, but it's white light and it's throughout the system, so you don't see it. But now you see my laser soared. Now you see the nice color. In a completely dark room, this looks fascinating. Okay? And you see that the width of this one is more at the beginning and less at the bottom because, again, Beer's law, because there is less light passing through at each successive layer. At the bottom, I do have a little bit of a light coming through. But again, it is because of a very specific absorption of green light by the dye, because if I pass red light through it, I don't see my sword. Right? So this sort of experiments, again, can be very easily and inexpensively shown using laser pointers, which you can always borrow. The green ones are a bit expensive, but you can always borrow and show that this sort of fluorescence emission can be very nicely shown. In fact, if you don't even have to make a solution, you can just shine the light on it, and the green light shows, red light shows up as red, okay, and green light becomes orange because it is absorbed and emitted in the orange-red region. Okay, very easy experiment. And the last one. Now we converted using the rhodamine dye. We converted green light into orange light. But now we are going to make use of hydrogen peroxide to generate light. I don't know how many of you have seen chemiluminescence experiment. Is there anybody who has seen chemiluminescence? Okay. If not, it will take me 2-3 minutes to set it up. Is that okay? Or shall I stop? Okay. So let me quickly take a look at the chemistry behind it. This is, of course, firefly, where there is a bioluminescence that you observe. So what we are going to do is to mix hydrogen peroxide, which is our fuel, with oxalyl chloride to produce the dimer of carbon dioxide, essentially. Okay, that's a very energy-rich molecule. If I don't do anything, it will decompose into 2 carbon dioxide molecules, one in the ground state, one in the excited state. But this loses energy by thermal loss. Okay, so essentially by losing the energy as heat. But I'm going to use acceptors which will transfer the energy, which will get the energy transferred from carbon dioxide, and instead will get excited to its first excited state. And now it will emit light, and these are all fluorescent molecules. They will emit light, and depending upon the choice of A, I can get light of different wavelengths. So today's experiment, I will use 9,10-diphenylanthracene, which will give you a bluish light. Rubrene will give an orange light. Perylene will give you a cyan light, and tetracene will give a, well, these two actually are fused together. Okay, I keep making the same mistake. This is not anthracene and benzene. It's a tetracene. Incidentally, that's pretty expensive. 100 milligrams is about 10,000 rupees. And all these materials have been supplied by Aldrich to me so that I can show such experiments to you. And tetracene will give the green color. Okay, so let me get into the act and do this experiment as quickly as I can. Are you sure you still want to wait for your lunch and see this experiment? Okay. So diphenylanthracene on the. So these are the 4 places where I'm going to do the experiment. This is 9,10-diphenylanthracene, and I need to wipe it in between. Second one will be rubrene. I assume this is rubrene. Yes. Okay. The third one is perylene. Perylene, in fact, is very stable and rather inexpensive. Perylene derivatives are used in various kinds of applications using the beautiful red-colored cars that you see. Paints are typically done with perylene. And the last one is tetracene, which, as I said, is very expensive. And I'm probably going to use about 500 rupees worth of tetracene here. All right? Okay, so this is done. Now I need one more dropper here. Yes, I am done. And very quickly you will see the beautiful chemiluminescence. I'll do these two a little bit later and this one first. my dichloromethane. I'm going to use a little bit of dichloromethane to dissolve this. I assume this is dichloromethane, right? Yes. To dissolve these dyes. Okay, 1, 2, 3, and 4. Can we have the lights switched off as much as possible? I will also dim my switched off. I'll also dim this one. No, off, light off, because we are going to generate light here, right? Okay, are you ready? So let me first add the oxalyl chloride to the first two, 1 and 2. Okay, this color changes, which means the oxalyl chloride is good. And now the hydrogen peroxide. Okay, blue and orange, as I said. Now I'm going to add, blue and orange are complementary colors. So if I mix orange to blue, it will become white. But then orange color disappears fast, so it will become blue again. So it is going to be white for a short time and then blue again, if it works. And this is still orange, because the orange has a shorter lifetime. So initially I have more orange than blue, so it is looking orange, white, and blue again. All right, so it worked. So diphenylanthracene, rubrene, and the last two, and that will be my last two experiments. Let me make sure I have got the right dropper for the right application. Now let me change the dropper. I'm not very sure if this is the correct one. Yeah, thank you. Let me use a fresh dropper for this. Okay, lights off, please. Again, I add oxalyl chloride here. Okay, since these are dichloromethane solutions, it has been kept cold, and now a different shade of blue and green. You see blue here, cyan, as I said, and this is tetracene, which is giving a green color. So even these two blue colors, as you can see, are different. The orange is already gone, but again it depends upon the sensitizer, and those of you who have studied a little bit of photochemistry and perhaps Jablonski diagram can rationalize some of these observations, and you can see that if you need to understand a lot of photophysics and also how these compounds get degraded as a function of time, because hydrogen peroxide, oxalyl chloride, these are deadly combinations of reagents. Okay, so with these very rather simple experiments, you can in fact demonstrate this principle of chemiluminescence and how, for example, chemical energy can be converted to light energy. So with this, I would like to conclude my session today. I'm sorry it took a little longer than what I anticipated, but I hope that you have liked the experiments and probably will use some of these for future reference for your students. But let me answer this question. You may not know, but you have heard about the Haber's process. This was one of the reactors Haber built in Germany, and this was used for 55 years and produced nearly 1 million tons of ammonia. Okay, I would simply like to end with a little bit of gyan to you, taken directly from Linus Pauling. I have a video, but I'm not going to play. One of the things about Linus Pauling is that he was working on the alpha helix problem or protein structure problem for 11 years, but he was not successful. And finally, when he was sick in a hospital bed in Oxford, with a piece of paper, he was able to sort it out. Okay, and therefore, message from Linus Pauling is never give up. All right. If you are unsuccessful today, even when you are in a difficult situation, please don't give up. And always keep your eyes open. And perhaps you all remember the very famous statement made by Pasteur, that chance favors the prepared mind. Right? Okay, finally, can I take one more minute? 2011 was the International Chemistry Year, International Year of Chemistry. 2019 is going to be the International Year of the Periodic Table. All right? And to celebrate that a year in advance, I am going to entertain you with my last, something that you already know probably. This is a periodic table song. How many of you have heard it before? Many of you. This was a song that was written by Tom Lehrer, who was a mathematics professor in Harvard in the 50s. Okay, so let's watch it with some animation. Oh, we don't see it. Sorry. Something went wrong. There it is. This has gone to an extended desktop. That's why it is not showing up. All right.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
With this, I would like to conclude because the secondary bromide has reacted, and the t-butyl chloride has also reacted. Okay, so that signals to me that it is about time that I shut up. Thank you very much.
The only source of knowledge is experience, is aptly said by Albert Einstein. This is what we experienced from today's session. Thank you, sir, for giving us insight into the topic, soft functional materials from bile salts, and the demonstration which has indeed helped we students to understand better. This will broaden our horizon on the comprehension of science. The session is now open for questions. I now hand over to Professor Gadre.
We are open for a few questions. So, if you have, please ask Uday. Uday wrote a very lovely set of articles in Resonance many years ago. So please read. If you have never heard of Resonance, look at it and you will find those very beautiful articles. But in any case, we are open.
Yeah, I'm in fact in the process of writing another one on Ronald Breslow. You know, he was my PhD supervisor. and he passed away a few months ago. So there will be a special issue of Resonance in April issue, and I will have a small write-up, and one of his 1958 classic papers will be reprinted. We just got the permission from ACS on that. Yeah, I'll be happy to answer questions if there are any.
It was so clear that possibly there are no questions.
Yeah. Yes. Okay, transition metals are not photoluminescent. Okay, transition metals also form gels, which is something that we worked on a lot. We use the transition metals to make gels and then make nanoparticles derived from the lanthanide transition metals. For example, we have recently made some manganese dioxide in a nano flower form and using that for oxidation of benzylic and allylic alcohols. So these gels also provide a support for making a variety of inorganic nanostructures, because the metal collared gels are the so-called metallohydrogels that we make. These are inorganic organic hybrid materials. So we are exploring various things with it. We don't know, we know how it started, but we don't know where it will end up.
Any more questions?
As far as the metallocollared gels are concerned, they are not reversible. Yeah, I forgot to mention that. For most small organic molecules, the gelation, the gels essentially become a fluid upon heating beyond a certain temperature, and that temperature can be tuned by the concentration and so on. But these metallocollared gels are all thermally irreversible except the silver collared gel. Okay. Yes, they are very sensitive to pH. Yeah, they are very sensitive to pH because, again, the bile acid has a particular pKa, and these pHs are these gels are formed only around pH 7.4. In fact, that's why the biological assay becomes so much easier for us, because we don't have to do any use any buffer. Because at a higher pH, what happens is that the metal hydroxide starts to precipitate, whether it is lanthanide or zinc or what have you, or any transition metal. At a lower pH, the carboxylic, the steroidal acid starts to precipitate. So we are kind of lucky, we have been kind of lucky that at about neutral pH the gels are formed. Yeah, this one. Instead of enzyme substrate, can you use anti-agent antibody interaction? We have not looked at it, but I think it should be possible to do it. But only thing is that, you know, we at least in the present form, we have been using the dihydroxynaphthalene as the sensitizer for antigen antibody interaction. Again, some other mechanism has to be devised that will trigger the luminescence as a function of either concentration or activity or what have you. We have not looked at that yet.
Hello, sir.
Yeah.
I'm Sachin.
Yeah.
Very nice talk, sir.
Thank you.
Sir, you did experience on black tea and green tea, sir.
Yes.
So, which is good for health then, sir?
Well, I'm not a nutrition expert. I don't even know whether these antioxidants that people say are good for you are actually good for you. Because, you know, one day you read something and the next day somebody else writes something exactly the opposite. I drink both. And, you know, unfortunately in these sort of things, when one individual is involved, you cannot really do a control reaction, right? What is good and what is not so good. So I drink black tea in the morning and green tea in the afternoon.
Yeah. Thank you. Uday will be available in the afternoon, and those who want to have more questions, we have an open session in the afternoon around 2:30 or something.
3 p.m. In room number 206.
Okay. You will announce that. By the way, I just wanted to remind you that there used to be a Linus Pauling film shown in this hall. Maybe we have those films, you know, real films. There used to be a projector room in the back, and we have seen all those very beautiful films by Linus Pauling.
I see.
I was very much reminded of many things about polling while listening to Uday in his very beautiful talk and demonstrations.
Thank you very much. Just one more before you leave. You see that the primary halide has also reacted. So it's not that the primary doesn't react at all. It just reacts very, very slow. Well, this is nearly instantaneous. This happens in a matter of about 30 minutes. This is much more slow. This is like fog in the early part of winter, and this is fog in Delhi when all flights are cancelled. Can I get these samples of the mirror images back somewhere here? If you like it, I can leave these samples with one of you. You can demonstrate in your classes. I'm also delighted to see that the first aid box was kept here. Okay, limonene is still... Okay, let me give this back to you.
On behalf of the Science Club, I take this opportunity to thank Professor Uday Maitra for delivering such a wonderful talk. Thank you, sir. I also thank IHOD, Professor Geji, the mentor of Science Club, Professor Gadre, and the coordinator of Science Club, Professor Avinash Kumbar. To all the audience for being present here, to Grey Eye Vision for the webcasting. I also thank those who have directly and indirectly involved in making this event successful. Thank you. All the students are requested to gather outside PCDA hall. There is an interactive session as a part of the Science Day. Thank you. All those who have written down the lecture summary are requested to collect it here.